Hi, I'd like to walk you through some of the example problems from Chapter 14. These are the ones right out of your textbook. Example 14.1. So a nominal 8-inch by 12-inch timber member, as shown, is used as a beam that is subject to a vertical load. The beam is oriented such that the 12-inch dimension is vertical. Calculate the section modulus of the beam with respect to the axis of bending. That would be the x-axis axis. So I wrote down, given the beam section shown, find the section modulus. Okay, so the first thing we need to do is to calculate the moment of inertia. So we'll go look the equation up inside table 3, inside the rear cover of your textbook, and the moment of inertia is 1/12 the base times the height. Okay, so we make that calculation. It's 951 inches to the fourth. Therefore, our section modulus is going to be I divided by C, where C is half of the overall height. So what this is going to give us is going to give us the max stress at the outer fibers. So H divided by 2 is 5.75. Therefore, our section modulus is 951 divided by 5.75, or 165.3 cubic inches. Okay, there's another way to solve this problem. Go to Appendix E in your textbook, Properties of Structural Timbers. Now, when you're in Appendix E, if you find the timber that we're talking about here, which is a 8 by 12, what we can do is look up directly in Table E1, that's on page 496 of your textbook, what the section modulus is, and they have it listed as 165. So, cubic inches. We could do it this way using the equation, or we could do it by looking up the properties in Appendix E. Here's another way to solve that. If we're talking about a solid rectangular shape, we can reduce the section modulus to this equation here, which is BH squared divided by 6. If we do that, again, we get 165 cubic inches for our section modulus. So, familiarize yourself with what's in the appendices. It's always good to know what's back there. Here's the next one. So, a timber of example 14.1 is used as a simply supported beam on a 16-foot span carrying a uniformly distributed load of 400 pounds per foot. Calculate the maximum induced bending stress. Neglect the weight of the beam. Okay, so given beam section from 14.1, L equals 16 feet, loaded as shown, which is 400 pounds per foot. Find the maximum induced bending stress. Okay, so the first thing we need to get is the maximum bending moment. Okay, I'm not going to ask you to do a shear and bending moment diagram for this problem, but I'm going to introduce to you the beam formulas in Appendix H. Okay, so in Appendix H, we have different beams set up, and they show us what some of the values are. Okay, so for instance, this is a simply supported beam with uniformly distributed load. Okay, this is number 1. Now this equation here tells us what the maximum moment is, which is WL squared over 8. So to find the maximum moment, we don't necessarily need to do the shear and bending moment diagrams. We need to be able to look up these formulas. Okay, so when we do that, maximum moment equals W L squared over 8. W is the 400 pounds per foot. L squared is the 16 feet. and divided by 8, so we get a maximum moment of 12,800 pound-feet. Our maximum bending stress, therefore, is going to be M divided by S. We calculated S in the previous example as 165.3, so therefore our maximum bending stress, that's small f B, is 929 psi. Okay, the next problem, example 14.3. Oh, the construction people made a mistake. They put the beam in the wrong orientation. Okay, what's our bending stress now? So, in which case, what I'm doing is I'm using this equation here. This was the one we calculated for a rectangular solid section to find the section modulus, and that gives me 107.8. The bending stress equals the maximum moment divided by the section modulus. Again, so this case it's 1,425 psi. If you notice, it's considerably greater than if we had mounted the beam properly. So 929 psi mounting the beam properly. If we don't mount the beam properly, that 929 goes up to 1,425. I'm going to pick up with another movie after this.